All right, now, welcome back, everyone. And now we're finally back for another lesson. And this week we're going to be talking about array plane intersections. We're going to start doing some intersections. About two lessons ago, I think we did raycasting. And now we're going to start using the raycast to start finding objects in our 3D space, basically the beginnings of collision. Um, So, uh, there's a lot of code changes that happened for this lesson, and instead of just going through the huge pile of code that really went to change, because I did a lot of cleanup and I added more new functionality since the last lesson, really just to get everything into the modules. Because like I said in the previous lesson, we kind of walked through a little bit of fungi being transformed into JavaScript modules. So instead of me going through every little bit of line of code just to show you where everything is, I'm just gonna put a link to the commit. Now I'll probably do this for every lesson. I'll make sure to commit just the changes, so this way you can see all the code changes for this lesson. Simple solution is really just download today's lesson and use fungi folder as your starting point. Unless you're following along and you want to build fungi, we're such at a point that we're at a high level that the little bit nitty gritty of the fungi framework is no point in talking too much about, like every line of code. I'm still gonna detail very specific points. So one thing, so like for example, I created the array module, and these are like two functions. I think either we just had a bunch of code and I just turned into functions, or I did make these functions. But this is the two raycasts, right? And I just want to point out some changes I did. Originally, to start off, build a raycast, because there's two ways of doing it. For points, to get the actual 2 points, the beginning and the start and end of the array, one of the first things you had to do to translate the 2D to 3D positions, you had to take the projection matrix and multiply it by the inverted local matrix, and then invert that whole thing. I was playing around with certain things, and I decided I know the projection matrix never changes at all. Once you set up the projection matrix, it never changes. So since the inverted projection is useful for point and mouse stuff, I thought, you know what, let me try caching the inverted projection matrix and see if I can multiply it by the local matrix. Well, like originally I had these swapped over, inverted multiplied by local matrix. And that didn't give me the what I was looking for, but then I just swapped it and it works perfectly. So why is this important? Well, because in this instance, I am multiplying two matrices and then doing an invert. So I can actually invert it without actually doing an invert. So by doing an invert, I basically use the exact opposite of each matrix and then multiplying them backwards. So that's basically what the gist of it is. So instead of using the local matrix or the inverted local matrix, I'm going to use the local matrix. And instead of using the projection matrix, I'll use the inverted projection matrix. And this takes away one step out of this whole thing. So if you're doing this every frame, there's this whole invert function is never needed anymore. So that's like an optimization trick that I kind of just messed around with, and it actually worked out pretty well for me. And also did another one here too. By creating this cached version the invert matrix. Same thing here. Instead of inverting the projection matrix, so I can then transform the vec, convert things into the 2D camera coordinates. Since it's cached, I save another one. So for both functions, I save one invert just by caching this at the very beginning when the camera is created. So I just wanted to point that out. That's an optimization. So when you're messing around with a lot of inverts, and think about ways of maybe you could, if you just swap things around, you might be able to save yourself a little bit of processor time. So yeah, I just wanted to point that out because every little thing you can squeeze out the best. So now back to the topic at hand. So ray to plane intersections. And, if you Google an image, you find a bunch of good examples that kind of illustrates a little bit of what we're talking about. The idea is that we're going to shoot a ray into 3D space, and we're going to find where it intersects, or you can say where it collides, where the line and the plane meets. Now, when I started reading about this type of intersection and I see these images, it made me think of how it is when you're dealing with 3D applications. When you're dealing with 3D applications, you say, okay, add plane to scene, and it basically just creates like a giant quad. It can have multiple vertices or just 4 vertices, but whatever it is, it's just like a giant quad. And to me, I was having problems understanding it because I kept thinking I had to find a way where, where it intersects, but it has to be within the boundaries, and that's not what ray to plane intersection is. If you're like me starting out learning a lot of this stuff, you might be thinking, like, especially looking at the images, you're trying to intersect with a square, and that's not what ray to plane intersection really is. To me, I guess a plane in mathematics is not what a plane is in 3D modeling tools. So a plane, I guess mathematics is an infinite plane. You can think of a quad that goes infinitely. That's what it is. This is just a representation of a plane, but when it comes to ray to plane intersection, it's the infinite plane. And a plane is defined by a position and a normal direction. That's why you have a normal. So the normal direction is really the plane. It's basically telling you where that plane exists, at what point it's like looking up. So, this plane is tilted down, this plane is tilted up. It's an invisible giant quad, if you want to think about it. That's what a plane really is. It's like a level, it's like a layer. So if you're like coming in like I am, you might get confused because the words mathematically and in other ways it's been used, they're not identical. So we have a plane, and like I said, I have a quad, but the plane is infinite. If you want to see this grid, this is the x-axis. This whole x-axis to infinity in both directions is a plane. Here's the y-axis. I mean, not the y, sorry. This is the z-axis. This whole thing is a plane, and it goes on infinitely. And if you remember our normal directions, for an x, the forward direction of the plane is z, basically. So, even though this is the x plane, the normal direction is this way. It's in the z direction. So our normal would be 0, 0, 1 as our direction. If I put like 0, 0, -1, then the direction is that way. So the plane is coming in this way. It's going in that outer direction. So this is the forward, that's the back. But if I were to change it to a negative, the forward would be back there, and this would be the back. So that's there you go. So that's a plane is defined by a point where that starting point is, and the direction that it shoots from that point. And any point within this axis counts. It could be this corner, it could be the origin, it could be that corner, it could be something over there. Any point that exists on this line and that in that normal direction is your plane. So there we go. So So let's move on. All right. So we're going to set up our array. We're going to set up our, oh, I did this backwards. Don't you love it? So we're going to set up our array. So we're going to have 2 points. And now we're going to visually see where our array is. I'm not using the raycast thing right now. I'm just prototyping. In this lesson, we're not going to use the actual raycast that I showed you in the beginning. Maybe in a few lessons, we'll start using the raycast along with an intersection so we can maybe draw points exactly where they are. So here's our testing raycast. So here's the start, and when it turns red is where it exits out. This is what we're looking for. And we're going through this plane. And it's not really an intersection within this quad. Like I said, it's this entire red line. Where in this red line does this ray intercept? So going on to the next part. So now to determine that, we need to start figuring out some things. Like, first of all, we need to know what is the delta between the ray. And we get the delta by subtract. It's kind of like the distance. We want the the vector length from start to finish. So if I were to do that, like, we don't need the norms. I was experimenting, but so refresh. What happened? Where did I break? I guess I am using normal. I'm not usually using it for the math. I'm just using mostly for visualization. Refresh. So that's just the normal. But what we want is the unit length from beginning to end, which is ray delta. And the ray delta is very important for us. So, I'll probably just get rid of that for now. There's more things that are more important. So the next thing we need to now determine is the distance between our starting point and our plane. So, like I said, a plane has a point. So we're going to use that point and that starting point. So if we refresh, so we have this new line that points directly to our plane. Now you might be like, why do we need that? Well, because we need to know how far the start is to at least 1 point on the plane. So we need to know at least 1 point on, like, the distance from 1 point. Because at some point we're going to use something called projection, and it's something I learned during this thing. It's a way of using the dot product to apply the length of one vector onto the length of another vector. But to get to a plane intersection, we need to get 2 lengths and then divide them up. So if we get 2 lengths and divide them up, we will then get this point perfectly. So we're going to go through each step and then see where all the values kind of like get visualized. So like I said, one of the first steps is that we need to find how far from the start of our array to some point on the plane is. So that's what we got. Get the distance. So now we're going to try to do some projection. So let's see. So since we got the ray delta, let's do the ray delta projection. So we're going to get a ratio, which is just a numeric value between the ray plane delta and a plane normal, right? So we're going to, so this normal based with the dot product, I should say this ray and this ray. Once we get those two together, I don't want that right now. So if we get the ray, we create a ratio. So with those two lines. And if we make a copy of our plane normal, the red line, and then apply a scale, it will give us the projection, and you'll see what the projection looks like. So refresh. There you go. So we took this normal, so it's a direction. We applied it to the start of our array, and this is the length. So the length between here to that point. So basically, by using that dot product, we took this line and this line and created this line. So that's what a projection is. We took that length and applied it to that unit vector, and it created this in the opposite direction going toward the plane, which is exactly what we want. So now we're kind of like almost starting to touch the plane. So we got that. So that's one thing. So we need that projection, this whole line projection is the first step, and this will be the numerator of our division. And if you want, we can see the other projection we got to do. And if you want to see the equation of the projection, it's vector dot n, which then, it's the dot product, times n. So vector times vector dot normal times normal. And that's exactly what all this code did. So now we're going to take the ray delta and the plane. So we always use the plane normal as the second value for the dot product. This way, we're kind of like projecting this length onto that normal. We're projecting that length onto that normal. And then we just reapply it to it. So at that point, now the normal we're going to project is this one. Our original ray gets applied to this. So when we refresh, we're going to see the projection. And if I was able to do, so ideally these 2 points exist on the exact same plane, essentially. So the plane that these two are touching are over here, and the other projection is they're both touching the actual plane that we're trying to get access to. So by using this and the other one, by doing a division, we will then get the ratio that hits the spot that we want to go to. So let's leave that alone. And we just comment that part out. And these two will do the job for us. So basically, I'm redoing this all over again. So I'm going to get dot product of our delta with the plane, or the distance from the start to the plane, and then our original delta length of our array. So you got the WP projection and the V projection. And K is really just our scalar, and WP divided by BP, which gave us a number between, I think it could be any number really. Ideally, it's going to give us a number between -1 and 1. But if you're undershooting the array, or like if there's no touching, you actually get a different value. So I have it commented out. So if K equals infinity, then the ray and the plane are parallel. If K is between 0 and 1, the line touches or goes through the plane. And if K is over 1, it stops before the plane. So you'll see an example of it equaling greater than 1. But either if it's between 0, if it's just greater than or equal to 0, you can still get the position that it hits. So even though if it's over 1, we will still get the I position, the intersection position. So if I refresh that, just like I said, just find these two projections that we just saw visually, and then divide them up to create a scale. Refresh. And if you can see, if I just do it, See how this line's kind of becoming gray? There you go. So this line becomes gray. And that point is exactly where we interact. See, the other side doesn't turn gray at all, but this side does. So that means that whole line it just stops right there, that gray line, because that is the point of intersection. And that's it. That is the whole intersection. Like I said, you use this or the projection between here and here divided by the projection of here to here, which kind of creates that halfway point, which kind of creates a kind of like a length that we can apply to our original ray to get the exact point. Pretty easy, I guess. I understand everything except why the division works. That's about it. That's all I can say is like I don't understand that part because I'm not a mathematician, but that's the secret ingredient right there. But I was able to visualize everything that you can. Now, all this code comes from I think it's George, sorry, not Jose. George Rodriguez. So this is the code he had, basically. And it's essentially, like I translated it to what we're doing here. We just take the start and end of the array. We get the delta between the plane position and the start of array. We get the dot product scale. And then to get the intersection, we just say ray start plus scale times ray delta. And that's basically all you need to do to get a ray to plane intersection. And just if you want to check to see if it intersects, you just check between 0 and 1. Now, now this is great if you want to test collision. But if you're looking for like what we're trying to do is like have like an editor tool and just poke something and basically have an infinite ray, you don't need to check for this at all. The only thing you would have to check for is if scale is greater than 0 or equal to or greater than 0. If it's over 1, it's okay, because we still, no matter what, we will still get intersection. We'll still get that position regardless. So if I were to, let's say, start messing around with our ray a little bit. So let's move our starting ray somewhere else. Oops, wrong one. I'm going to use this set of coordinates. Refresh. See, now our array, let's see if I got to line it just right. Now our line array goes here and it stops right before the plane, and you kind of see this little gray line that continues, because even though like right here, right, it says k equals 1.2, it's not between 0 and 1. That means it cuts short. So if it's greater than 1, it's right before it hits. But you can still get the position regardless. Like that if statement, that check at the end is just to see if there's a collision. But like I said, if you're using this for mouse clicking, you don't need to check for collision. All you need to do is make sure it's greater than or equal to 0, and then that alone will give you your coordinates. So the coordinates is 0.25, 0.60, and that is the position that it connects to right there. And again, that's just one of the projections we have visually. And just for funsies, so we stop poking at that square. Let's move our ray even far away. Now it's all the way over there. And it's still cut short. Again, but like I said, it goes and it touches right there. Even though it doesn't look like it if I just turn the camera just slightly. It's hard to get it just right. But trust me, it does intersect, even though it doesn't look like it does. It's the projection matrix making things look like they don't touch, but it really is touching it. So this point is the point that it intersects. So yeah, you can point this at anywhere over here and point it in this direction, and you'll get it. And it's just 4 lines of code that does it for you. And I just want to say that George Rodriguez, he had a great video on plane ray to plane intersection. He goes deep into it. Like, he actually goes through the mathematics, how to formulate the equations, how to put all the equations together, and then canceling everything out. So that final equation you see in the code is really after you do all the mathematics, like basically all the proof of the mathematics is done. So if you really, I'm going to post the link to his video about it, and probably also post the video to projection, so you can learn how projection is done, because it's important to finding the intersection. Those 2 videos together will help you understand the mathematics behind it. I probably didn't do a great job of illustrating it, but this guy does a pretty good job. I should say decent. Does a really good job of explaining the mathematics behind it. He really knows his stuff. He's definitely worth subscribing, because he has a lot of great math tutorials that are geared toward game development. I'm going to probably spend hours upon hours, and the video about ray to plane intersection, I've probably seen it like 8 or 9 times. I kid you not, because I really wanted to try understand the math, and I just kept watching it and trying to poke at it and understand it. And as I was watching it, I was writing the code to see where the numbers are, see where the equations are. Like, I just kind of stepped through like seeing where the projection values go. I'm a visual person, so to me, to be able to see where the numbers are makes it a little bit easier to understand. Like projection, I totally understand how projection gets it. Now I know another use for the dot product. It's really cool, and it could be pretty useful when you want to project the length of one vector into another. So yeah, it's pretty cool. And just by proxy, coding math is a great one too. I highly suggest you subscribe and watch a lot of his videos. And if you're really into C++, I definitely suggest Cherno. That's a great, another great YouTuber that teaches you game development, not necessarily math, but all the C++ stuff you can imagine that you'll probably need to do for game development. This if you're doing web development, not web development, game development with C++. So yeah, and that's it for this week's video. Or I might do 2 videos this week. Hopefully this one's a kind of a short one. And so I hope you understand that that's what a plane is that infinite square rectangle. And hopefully if you watch George's videos, you'll understand the mathematics behind it. He really goes really good in depth with it. So I really suggest you watching a couple of the videos, watching those videos and playing with the code to really get an understanding of this. For the next lesson, I'm continuing intersections, and we're going to start maybe doing triangles. So this way it won't be like this infinite plane. It'll be actually triangles. So if you point it outside of a triangle, then it won't intersect at all. It'll be bound by the triangle itself. But this part, the plane intersection, is probably one of the most important aspects of intersections, because even for triangles, the first thing you got to do is find what plane that triangle exists in. You have to determine its normal, which I'll step you through, because right now I just guessed the normal and then got a plane. But when you're actually trying to do this, you need to actually find where the normal is if it's not given it to you. So that's going to be in the next lesson. We're going to do normals. Discovering normals from a triangle, and then using that point and that normal plus what we learned here to then find where in what plane that triangle that exists in is there an intersection, and then by using that point of intersection, testing to see if it's within the bounds of that triangle to find that true or false. Did it intersect that triangle? And once you can do a triangle, you can do a quad. You can make a square and then just intersects two triangles basically. You just test it twice. Every quad, you just test the quad twice. Did it touch it? I tried to find information. I couldn't really find one for a square. And this wouldn't be called a square or a quad. It would be like a ray to rectangle or ray to square intersection. I couldn't find information, but most people just say they just do two triangle tests to do a quad. Another one would be polygon. There's a ray to polygon intersection. Would be like bare minimum 3 points, but that's a triangle. But then you can have 5 points, 6 points. You can have this odd shape as long as all the points exist on the exact same plane. That means they have all the exact same normal. Then you can do array intersection just fine with it, because else you would have to break everything down into triangles and then do a intersection test for every triangle within the polygon. So yeah, then there will be spheres. There's discs. A disc is a similar. It is a disc is a circle. So you would have to you will have the center point of the circle, and then you have to discover its normal. And once you know it's normal, you do the exact same thing. But then the point that you find in the disc, you would do a distance check. If the distance from the center of the disc is greater than the actual radius of the disc, then there's no intersection. So there's a lot of tests to it, but the test of every single intersection starts off with a ray to plane intersection. You always have to find the plane first, then you can then find some point on it. Then you use that to test the bounds of any other shape that you're trying to intersect with. So once we get all the flat geometry out of the way, then we'll start dealing with squares, like bounding boxes, and spheres. And that will probably end all the intersection videos, because that's pretty much all to it. At that point, you'll have all your flats and then some 3D geometry. So that'll be it. So yeah, like and subscribe, and see you guys in the next lesson. I hope you had fun with this one. Bye.